Hi guys, here's a continuation of the notes on chemical reactions. We are at the letter C, rates of change. It's the second part of the notes. Rates of change in chemical reactions. So there are a lot of factors that can influence how fast chemical reactions happen. Obviously, sometimes you want a chemical reaction to take place really fast, and sometimes, like in the human body, you actually want a chemical reaction to slow down a little bit because if it happens too fast, it can generate too much heat and it can damage the cell. However, there are some examples on the screen here of various things that could have an influence on the rate of a chemical reaction. And basically, you guys, when we talk about rates, that refers, of course, to, how fast does something happen? So if we think about it in terms of the particles, remember that anything in terms of reactants and products are made up of particles. And if you influence how often those particles collide with each other, then you're going to make a change in how fast a reaction can take place. So on the screen here, a couple that are emphasized on your notes over on the far upper right here, increasing the temperature of a reaction. This is very commonly done. Um, Increasing temperature makes the particles move faster. It increases the amount of energy and therefore it increases the number of collisions. Increasing surface area. Increasing surface area is over here down on the lower left. And again, this is a pretty easy one to visualize. I mean, if you thought of a sugar cube dissolving, now dissolving is not a chemical change, but it does illustrate the principle for us. So just bear with me here. If you had a really big cube, you only have a limited surface area exposed to the water. So it's going to take a lot longer. If you break that up into tiny pieces, now you have increased the surface area and you have increased the frequency of collisions. And therefore, that reaction would take place faster. So go ahead and make that analogous to breaking up a chemical reactant, something that was actually reacting into tiny, tiny pieces. If you do that, you're going to allow for more of those collisions to take place. So another one that is kind of interesting that we're not going to spend a whole lot of time on, but increasing pressure will also cause a reaction to take place faster. And that just, in that case, you're kind of pushing particles together. If you increase pressure inside a reaction vessel, you're making it so that there's nowhere else for them to go. And so they're going to start to bump into each other more often, and that's going to increase the reaction rate as well. Another really obvious one that is sort of illustrated here by collision theory, stirring or agitating solutions. Obviously, if you stir or agitate something, you make it move. Again, you're increasing energy and you're increasing the number of collisions. So these are the things you want to remember. You can increase the temperature, you can increase the surface area, you may stir, you can actually increase pressure. That makes it so that those particles bump up against each other more often. Moving into something new, you can also use a catalyst. Now, a catalyst is something you're going to talk a lot about these in biology when you take biology, but a catalyst is a protein in a cell that changes the rate of a reaction without itself being used up or entering into the reaction. Now, a catalyst in a biological system is known as an enzyme, but we can also use catalysts like in general chem as well. But the ones inside the body, you need to remember that some of them actually speed up reactions and some of them slow down reactions. Catalysts aren't reactants, nor are they products, and they do not enter in, and so you don't write them in to the equations in any way. You might put a little symbol underneath the arrow showing that it was present, but it's never going to show up on the product side. Inhibitors are kind of like the opposite in a way. If you have a catalyst or something that's actually going to promote a chemical change, an inhibitor actually prevents a chemical change from happening. And it's like some of you who might be interested in cars, you might have heard of a rust inhibitor. In fact, if you go through the drive-through car wash, you'll see that as a selection. You can actually get rust inhibitor. Well, rusting, you guys, is a chemical reaction. And a rust inhibitor prevents rusting from happening. An inhibitor will bind to a reactant in order to prevent it. Another great example shown on the screen here. Some of you who are into cooking might know that you can add lemon juice or vinegar or salt or soda water or any number of slightly acidic, generally, substances that can prevent the browning from taking place from cut apples. Like if you're making a fruit pizza or something, you wouldn't want to put the apples on there and have them get brown. Finally, equilibrium is important. It's important to note that some, but not all, chemical reactions are reversible. If I talk about reversibility, it just means that they can go forward and they can go backward, and sometimes this is like kind of simultaneously, like you'll have the reaction will move toward the product end, and then it'll move back to the reactant end and back to the product end, and so on. That is not typical. Most of the reactions we study are one direction. So if you think about a reversible reaction, equilibrium is reached when forward is equal to reverse. But in a typical reaction, as shown on the table below, it can also be reached when the amount of reactant and product doesn't change anymore, and it's static. Once they get to that point where they're no longer are there any reactive surfaces present, that's going to be equilibrium.